Hi there. Elementary algebra, the way it's presented nowadays in high schools and universities, is actually very perplexing and full of inconsistencies. So let me show a few examples. To start with, we'll consider matrix multiplication. And what you learn early on, that when you multiply a matrix by a column, let's say it's a matrix M and a column is called V, and you get a new thing. You get a V prime. Then to calculate the coordinates of V prime, what you do, you say that actually its coordinate will be, if we do the convolution of J, and we sum it over J, right? And what you learn that the same indices are close one to each other. On the other hand, what you usually learn when you work with bases, and especially when you work with transform matrices, if you have two bases, let's U and W be bases, the way and you actually to pass from one to another, you use a matrix T. What you learn that, for example, if U was the old basis, then the way you write the new one, that W, we take a vector each, and to calculate it, we take a matrix T. We are summing, actually it's J, it doesn't matter. If we take J as a vector, you do convolution over E, and here the E right and left side and J on the E right and left side and J on the right side, you take a sum over E. And the problem there, actually adjacent indices are not the same one. And anyone who has a little bit sense for aesthetics must feel a deep suffering and psychological resistance when he sees this formula. And there is a easy fix. We need just to accept that we write scalars on the right side of vectors, right? Well, and then if you rewrite our formula, it is much better. And further on, we'll see more examples why you should write on the right side. Another huge problem is the transfer formulas for different geometric objects. Usually, students suffer a lot. Teachers are in much better position because they've been teaching the matter for a long time and they can deduce all the formulas in real time, while students really can't. When I was in first year of university, the way I did, I always wrote each time commutative diagrams and try to see which way we need to multiply matrices on the right side, on the left side. Why even we need to multiply on both sides, why can't we do it on the one side? I've been thinking for several years if there is any better solution. I read different books on linear algebra and algebra in general, and in two books they will mention right now. The first one is called Algebra and is written by Weinberg, and the second one is a book on linear algebra written by Nikolai Vavilov. The last one, I don't think that is translated to English, though. I saw the following convention. If you have a basis, so let's B be a basis, and V be a vector in the same space where we have our basis, then actually we can write V as a row B multiply by a column of coordinates, right? Have the multiplication, and actually the convention of multiplication row by column, it works here. And what you get, if you do it, you get a sum of bj times vj, right? It's sum over j. And as you can see, actually the scalars which are here, they are in our field, they're on the right side. And that means that we're actually working with the right field. We can rewrite everything on the left side, but it's a little less conventional because then we'll need to write our matrices on the right side. Yep. And we'll need to write, instead of columns, we need to write rows. And this way we're stepping a little further from regular linear algebra. And why this formula is superior? Why should we write things in this manner? It's because whenever you have a new basis, which letter is now really taken? Okay, we'll take W. If W is a new basis, you take a transform matrix, and actually you write new vectors as a new combination of old ones. And the way you write it is actually the new row is t multiplied by on left side, sorry, by the old row, and it's b1 up to bn multiplied by t, right? Again, we multiply on the right side by coefficients, and then if you have this line, what you can do, you can go and multiply everything by the inverse of t, and you get w times t equals the inverse of t equals to b, right? And then the only thing that we need to do, we need to put it back here, do a substitution, which is completely algebraic operation, which will be new basis w1 wn inverse of t and all coordinates. And if you do those calculus, you get a new coordinates, a new basis. Really, really simple. So instead of thinking which thing is which, what we do each time, and writing sums, we're just using matrix multiplication, and we do substitution. Very simple. And then I thought maybe we can do a similar thing with dual bases. Maybe we can do a similar thing with matrices, with bilinear forms. And actually we can do. And this is what I've been working a year ago. I worked for a week, and I got a really decent new convention. So the first part, we need to talk about the dual bases. If you have a basis B, then you make its dual basis that will write as a column, and actually each bi star is a projection when you take, for example, the form a space, right? You have a space, and actually the space is decomposed into subspaces. It will be vector of b1 or bi, and you sum over I, right? And to each such decomposition, what you can do, you can have projections. And actually its projection, we call it a dual element of our basis. So, and this is associated to the sum, to the basis, right? The next thing that we observe that actually if you multiply bi star with bj, you get a connected symbol, which means that is 1 if they're equal, and 0 if not, right? And if we write in the matrix form, we take b1 bn multiplied by a column, Jesus Christ, we go write the dual elements on the left side, b1 bn, and if you do convention, multiplication line by column, you can do it in this case, and what you get the identity matrix, right? So it's an alternative way to write it, and the way we'll write it, is b star times b is an identity matrix. Great. Now if we want to incorporate the change of basis, what we do, we say that, for example, if we go from b to in uw, we learn that to get it, we write w as b times t, in the sense we discussed earlier. And then if we have its dual basis star, actually we get it from the old basis with another matrix that we call C, for example. And what we know that if we multiply, we need to write on the different side, because now it's a column. So it will be b1 star bn star times c, or just simply c times b star. And what we know if we multiply w star with w, on the one side we get identity matrix, on the other side we get actually, if we do the substitution, we get c b star b t. Here we get identity. Identity disappears, and we get just c times t. And c times t equals identity means that actually c is the inverse of t, right? And now when you have a transform formula for dual basis, that actually we go and take an inverse matrix. Again, we didn't really thought about anything. We didn't write any formulas, any convolutions. We just used matrices, matrix multiplication, and properties of being inverse, and we got the transform. Absolutely better than usually what is done at universities. Right, we have a dual basis, but for example, what we do with what? So, for example, if you have a linear form, your linear form was written in one basis. The way we write the linear forms are lines. So linear form, so it's one form. You get, for example, L1, Ln, and multiply by the basis, B1 star, Bn star. You get a form. And if you want to use a substitution formula, the transfer formula, we actually write the B star as W star times T. Jesus Christ, it's the wrong side again. It's T W star. We put it here, and we get L1 Ln times T W star. Easy, and we have a new formula with new coordinates and new bases. So what about if we have whenever we have operators? So like, let's have operator phi go from E to V. Then, and here we go, we had a basis B that we transferred to B star with T, and T1, and here we got C that we transferred to maybe TB, to C prime with TC. So what we say usually, if you go and apply phi to each element of a basis, you have a linear combination, so you get a sum of I of, we take new elements Ci, and we have its coefficients. So let's call them actually Mij, right? Again, the same, this is one next to another. Oh, we need to rename things. For example, if we go and say that we have G here, now it's all right. And that actually, and then it acts linearly. That means that actually if we take a restriction of phi on vector space generated by this basis element, where actually what we have this thing multiplied by anything that gets out of dual element of J, right? And then as we have a direct sum of subspaces, actually we can pass to phi and say that actually phi is a sum of J of sum over J, Bj star. And actually the way we can write it as this line. Multiply by column Bj. B1, Bn star. And actually this one we can write it as our basis C1, Cm multiplied by our matrix M, right? And now you see the space for, again, for substitution. If more simple way to write it is Cm B star. So whenever you want to write a new basis, what you do, you say that a new basis is how we go and say that is O times Tc, B prime is B times Tb. Then if we write this way, we say that C is actually C prime times Tc inverse, B is actually B prime Tb inverse. And then if we go and from here, for example, we say that B star is actually Tb of B prime star, gray. And what we do, we plug it back, the two, and we say that a new basis, here we substitute for C prime T minus 1C, here we write M, here we write Tb B prime, and this is the new matrix of our operator in new bases. And exactly, it's precisely what you learn at universities. And this is a reason why we need to multiply on both sides, because actually when you pass from matrix to operator, you multiply a matrix by column and row of basis elements and some dual elements on right and left sides. Right, and finally we get to place when we'll do what we call it a bilinear form. So it's two form. What we do, a similar construction, we actually say if we have a bilinear form, we get it matrix. And as we plug vectors on the both side, right and left, we need to multiply by dual bases on right and left. You can multiply by basis B star on the right. And actually, if you multiply by basis C star on left, we can't really do it because it's a column. We need to take a transpose. Now we learned that actually to change bases, we'll multiply by just by matrices, C prime star, and you basically get by substituting CC, C prime star M, TB, B prime star, right? And you have transpose here. You apply transpose, and you get a new basis transposed right here, like here. You have TC transpose M, TB, B prime. Great. And then everything really works. And I want to show you why this notation even makes sense, because if, for example, here we go and apply phi to what we got B1 Bn V1 Vn, or simply V, then what we get new basis C times matrix times B star. Then here we get, so it's phi, and here we pass to V, and V is actually is B times let's call this column, let's recall it V, the big V. And here when you multiply, actually those things disappear. You get identity here, and the only thing is left is C times MV, and MV is the coordinates of V after you applied an operator, and they're multiplied by C. That means they're the basis C. And actually, you don't really need to have a similar things here. If you have a basis B prime, you get a different matrix, but actually if you do the computation, everything still be fine. And this way, instead of drawing commutative diagrams, instead of working with sums and convolutions, the only thing you need to do is to know that actually operator is a matrix multiplied by left right side by some basis and dual basis elements, and then you do substitution. So I hope this will help you. They'll give you some ideas. Maybe you may want to try to extend this theory to tensors of higher rank. But then what you need to do, you need to take, instead of basis, you need to take a tensor product of bases. So it's a little bit heavier, but it's still doable. See you next time.